Now we're going to have a look at the Raspberry Pi, the Adreno, and how we program these two sorts of devices. Okay, looking at the platform, we have two very different processing platforms that we use, and they're for two very different purposes. We're using an Adreno Uno. The processing chip for this particular device is an Atmega 328. This is around about $35. Probably not the cheapest one we could buy, but it is actually quite suitable for prototyping and the kind of work we'll be doing. The processor itself runs at 16 MHz, which is middle of the road for a microcontroller. Importantly, it has 14 digital input-output pins, 6 analog input pins, 6 pulse width modulator pins, and I'll explain about those in the next session, and 1 UART that we use for our serial communication from the computer to the device itself. We're also using the Raspberry Pi 3. These are about 50 Australian dollars, a little bit more expensive, but they are a full computer and they have a much higher specification. However, they have limited input-output pins. So the Raspberry Pi 3 we're using is a 1.2 GHz 4-core processor, so it means it has 4 computers on the one chip. There are 4 CPUs within that one piece of silicon. It has 1 GB of RAM, 4 USB ports, both Wi-Fi and Bluetooth for communication. It has SPI and I2C buses, which is the kind of communications that we use to talk to the other microcontrollers. So we can chain up multiple Adreno type processors, which are then attached to sensors, to this one control board that can handle the communication. The operating system is loaded onto an SD card, and that's also our storage, so it acts like a hard drive in a normal computer, and it has video output and audio input. There's some images here of some of the different configurations you can get these devices in. On the far left is a group of Adreno type processors. The Uno we can see is the bottom right one there. And we can get ones that are physically much smaller, and also some that are a little bit bigger and a little bit more powerful. We can see the Raspberry Pi that we're using in this image as well. The Raspberry Pis come in several flavours as well. We're using the Pi 3, you can get a Pi 2, model A and B, and also now the Pi 0 and a Pi 0W. The numbers basically mean their capability. So a Pi 0 is an absolute minimal system. A Pi 0W is a minimal system but has the addition of wireless. The Pi 2s were one of the earlier iterations of the device. So they're the hardware platforms we'll be using. Now let's have a look at the programming, how we actually get these pieces of hardware to do things. Right, programming, don't panic. It's not going to be as hard as it normally is. We're going to be using a graphical language. We have Python available if you want to use it, but the graphical language is probably the more logical way for our purposes. We're not here to learn how to program, we're not here to learn the syntax of a particular language. What we want to do is learn how to create IoT devices, how to collect data from sensors, and then how to, very briefly, process that data that we've collected. We're going to use the Wily Adreno platform to control the Adreno via the Raspberry Pi. So we'll program the Raspberry Pi to actually talk to the Adreno for us and then read the sensors. In the meantime, the Raspberry Pi will be capable of communicating back to our network and up into the cloud if we so desire, and in one of the later labs we'll have it talking to an Android tablet. So in programming, what have we got? Well, first of all, I'll just explain a little bit about Python, just so you know where we're coming from and why it's quite commonly used. Python has a very simple syntax, which means it's easy to learn, it's easy to understand, and it's easy to write. It's interpreted, so it's not compiled. We don't run a separate program to turn it into our written language, which we understand, into something that a computer can understand, a compiled program. It reads each line and interprets each line, turns into machine code as each line is read, which means it's very sequential. This is good in some ways because it's easy to debug and it's easy to develop your program, but it isn't the most efficient way of doing things. A compiled program is generally much quicker in its runtime, much more efficient. It's also open and cross-platform. So I'm running on a Mac here. I can run the same Python program that you write on my Mac, whether you write on Windows, Android, and whatever other platform that you care to name, such as Linux. So that is a big benefit. Write it once, run it many places. However, for our purposes, it's probably an overkill. Unfortunately, we don't know what background you've come from, so we're going to have to run through stuff as if you haven't programmed before. Alright, so here's a little example. When we're using the Adreno IDE, this is the integrated development environment we use to program the Adreno processors. It appears as a small window, as we've got shown here, where we see orange words. They are a routine in the Adreno library. So these are pre-written parts of the application that will handle fairly standard things like printing text out to the screen or reading a pin on the Adreno, writing a pin on the Adreno. So we don't have to know exactly how that works. We've got a library of routines which will allow us to interact with the hardware of the Adreno without knowing how it's actually being done. These first two lines in blue, constant int, basically just replaces numbers with names. So we prefer names of things rather than numbers. So we can say that the string switch pin equals 2. That means every time the program sees the word switch pin, it just replaces that with the number 2. Easier for us to understand. That's really all it's there for. Each pin we need to set up for a purpose. It's either going to be input or output. And where we look at the orange text further down, we've got primary mode, motor pin, comma, output. Output is a keyword. That's something that's within the programming language itself. We're saying that this particular pin, called motor pin, is an output pin. And if we look up there, we've actually got constant int motor pin equals 9. So that would then translate into this pin mode, number 9, pin 9 on the Adreno, is an output pin. So we're going to write out from it. We have to define these sort of things. Next down we have the loop, which is the main program, and it's just loop with a bracket, which means loop forever because there's no conditions to be met. And we'll talk more about loops a bit later on. We then read the switch. If the switch is on, high, we switch the motor on, and if it's low, we switch the motor off. And down at the very bottom of this area, we've got a console area for printing out text that we want, such as messages and perhaps what the temperature is, which is things we'll do. So there we have the syntax laid out, and it's explained in there, and you can have a look through. We're not going to worry too much about that, but the idea behind using the graphical language is that we don't need to understand the syntax, and that's really why I'm showing you this Adreno IDE. We don't need to worry about it unless you really want to get into it, and we can do that too if we've got time. So the language we're going to use is purely graphical. It comes from something called Blocky. Now Blocky is an open source programming environment. We can go and have a closer look at that. I point to some of the help pages on using Blocky, and it's implemented in Adreno as the programming environment. So what we have here is an example, and it's a fairly good example because this simple little jigsaw puzzle piece said Adreno on port dev/tty ACM0 is a little bit clearer. It may not be crystal clear, but it is a bit clearer. We're going to start the Adreno on port, and this is where we've actually connected it to, and it'll just be the USB device, and configure it so that the Raspberry Pi can then control it through the Adreno environment. So this simple start Adreno on port actually covers all of that section in text on the left. And as we can see, there's quite a bit there that we have to set up. We define the set board as board type and port, so we're saying what type of board, which type of Uno we have, and on which port it's on, which connection it's made to, etc. We have these very simple blocks that replace these sometimes complex statements which can be a little hard to understand. So we'll look further again at Blocky, but basically it is just a much simpler way of writing your application for prototyping purposes. It is not the most efficient way to write your software, but it will get you up and running and you can try things out. So the next thing we're going to do, as we're going to write a program to look at the environment, we're going to have to sense that environment, so we need sensors. Sensors are devices that can detect an event from the physical environment and respond with an electrical or optical signal as an output. We've got some kits there that you can use and play around with. We'll only be using a few components of it, but it has a fairly large array of sensors within it. You can have a bit of a look at those. They are very simple sensors. They're very, very inexpensive, but we can actually do quite a lot with these. And there is a very large set of sensors available if you have a look on the web. I'll make a point here. Quite often talk about using Wikipedia as a quick reference. Wikipedia is great as a quick reference. I found it's a wonderful place to start looking for things, but never trust a single thing you read on it. Remember, other people can change it. But Wikipedia is not a bad place to start. So we're going to be using the temperature sensor within our lab experiments today. What we also need to do is, if we're going to read something, we want something to happen. So we're going to make things happen using actuators, relays and motors. In our case, we're just going to be using the servo motor and the straight DC motor. but there are other actuators you can use. Actuator is just a type of motor that is responsible for creating movement. Simple. Our kit contains a couple of types of electrical actuators, and these will convert electrical energy into mechanical torque. We don't have any relays in there, but relays are just a switch. So a switch that we can turn on or off from a signal. We're going to be using a field effect transistor, and we'll go into that in one of the other sessions, to act as a relay or a switch. So it'll be the same sort of thing. Alright, so we'll play around with those very shortly. Some additional tools we can use is Packet Tracer. Packet Tracer is a simulator for networking. It has extensions which allow us to do simulation of end-to-end IoT systems. It runs under Windows and Linux, unfortunately not fully under Mac yet, but hopefully one day it will. And it allows us to build little I/O devices. We have displays and sensors that we can build in. We can check the connectivity of these things, and is mostly used for simulating traffic conditions. And that's what we'll be using it for. Alright, so we've got our sensors. We've written our program to write out to the actuators, so we're going to get some movement. In our case, we're going to have a little temperature sensor that will indicate the temperature and turn a fan on and off if it gets too hot. But we need to communicate this information to our cloud storage for it to be truly big data, or an Internet of Things device. There are a lot of different connectivity devices around, and each of them has advantages and disadvantages. First one we're looking at here is Zigbee. Zigbee is a low energy, low power, low data rate wireless protocol specification used in personal area networks. It has utilization acceptance in home automation and some other areas, but it has significant flaws which mean it's not that applicable or that suitable for many serious, no, not serious, for many sensitive Zigbee is a low energy, low power, low data rate wireless protocol specification used in personal area networks. So these are normally networks within a 1 or 2 meter range. It has utilization in home networks, home automation, but has significant drawbacks which makes it unsuitable for many sensitive or demanding applications. First one, of course, is its very low transfer rate. It has a raw data rate of 250 kilobits per second, but that is not its throughput. The throughput is much lower, particularly when you get large numbers of Zigbee devices in the same area. Zigbee works by using application profile identification numbers. These identify the manufacturer and the type of device that is being communicated. There are some private and some public profiles that we can use. Early versions of Zigbee, as I said, have some serious and exploitable security vulnerabilities. Most of these relate to attempts to make it easier for people to use, so it doesn't have authentication. And you just can connect to the devices, and that means if you can just go and connect, it means you can write to them or read from them, and that can actually lead to other exploits within your network. So it is useful in some circumstances, but be aware it does have these significant limitations. Probably a better technology for most users is Bluetooth. Now, we should all be fairly familiar with Bluetooth headsets, Bluetooth mouse, Bluetooth keyboard, really devised as a replacement for cabled I/O, such as your keyboard, as I said. It's a wireless protocol, again, used for personal area networks, generally only up to 10 meters, but you can get some implementations which will reach much further, 100 meters or so, but that's not what it's designed for. The latest one is Bluetooth Low Energy, BLE. Still operates in the 2.4 gigahertz ISM band. That's the industrial, scientific and medical band. It's free to use, doesn't require licensing, etc. Has a very fast connection rate, so it will connect to other devices very quickly. The pairing process is fairly quick, in a matter of milliseconds. Relatively high data rate, up to 1 megabits per second, but again, it is the data rate that is 1 megabit per second. That doesn't mean you will actually get 1 megabit per second transferred through the system, particularly when you have more than one device in the Bluetooth network. As the device numbers go up, there's greater contention for the media. Everyone has to have their shot at talking. We'll talk about networks a bit later on. And that reduces the actual throughput you get. And in actual fact, when you get to around the 10 or 15 sensors, your data rate will fall to somewhere in the hundreds of kilobits per second, rather than the full megabit. BLE devices can go to sleep, which means they have significant power saving. You can have a small Bluetooth device that's transmitting once every few minutes. working off a coin battery, one of the small watch type batteries, that will last for years on that same battery. So Bluetooth BLE, reasonable data throughput rate. It has some security issues, but most of them are being overcome or have been overcome, and a reasonable data rate. Moving to sort of what I would term top of the line is the 4G, 5G. This is our cellular-based systems. We can take advantage over the normal communication system. It has two types of bandwidth. There's high mobility. This is when you're a car, train, traveling rapidly with a 4G system, and that can have 100 megabits per second, which is great if we've got very large amounts of data. Low mobility is extremely fast. The 4G goes up to 1 gigabit per second. The disadvantage here, though, is that because they are fairly high data rate, they are also fairly long range. They have a fairly high power consumption. So you only want to use these where you have a consistent power supply. Perhaps not the best suited for battery-powered devices unless you have a fairly large battery, such as your mobile phone. Long-term evolution, or LTE, and WiMAX are two popular 4G systems, and they actually have specifications for the IoT, so that can be worth looking at. 5G still under development, making progress, but we won't talk too much about that one. So 4G and 5G are a standard network technology, the one we use with our mobile phones, for example, and it's well established, but high data rate means greater power consumption, may not be suitable for all applications. There are others that are specifically for the IoT, and the one we'll just mention here, there are a couple of fairly common ones. Fox is one, LoRaWAN is the other. LoRaWAN is a wireless technology designed to provide wide area network connections to power restricted devices. So here we have something that is specifically designed for long range but low power. And of course, if we're going to have long range low power, it means that something has to suffer, and that's its throughput. The data rates range from 300 bits per second, which is really, really slow, to 50,000 bits per second, 50k bits per second. So this is a very low rate communication protocol. As I said, the advantage is it is long range. LoRaWAN networks can cover several kilometers, but as I said, data rate very low. It has security implemented throughout the stack using a multi-layer encryption scheme, so it is secure, and looks to be one of the technologies that will be the way things head. As I said, it's not the only one, but it's just one worth mentioning. So each of these technologies for connecting our IoT device to our cloud have advantages and disadvantages. And three main attributes are data rate, power consumption, and range. And usually, at best, you can only get two of those three the way you want them. So you'll either have long range, high data rate, but it will consume a great deal of power, or you'll have low power, low data rate, short range. Okay, so that's it for the introduction to the devices and the technologies we're using. Let's go and build some IoT devices.